All right, so we'll just get started. So, good morning, all of you. So today, my plan is to just teach you a topic which is it's not very hard as such, but there are some applications when it comes to making decisions when things are uncertain. Right? So it's the kind of thing that we always face, right? We don't know what's going to happen, but before some event happens, we have to make a decision on things, right? So this is actually the framework of decision making under uncertainty. So a lot of policies or government decisions, even that also could get. These are the kind of techniques that policymakers can use. Right, so it's very closely tied to the notion of base nets. So that's why I thought I'll do it along with this. And also in your labs, the final question, I mean, not the additional question on base classifier, but the Berkeley question, the last part has something to do with these decision networks. So that's why I thought I'll do it now so that you have some time to work on it. So these decision networks are, like kind of like base nets, but not exactly like that. So what happens is there is some action to be taken, and there is some utility. There's some kind of a utility node which depends on a random quantity. So this weather is a random event. So I'm just taking one example. So how can the weather be, right? So that you don't know beforehand, and before you know what the weather is going to be like for the day, maybe you have to decide whether you want to take your umbrella or you want to leave it at home, right? And there's a utility associated with all of these. So there's some utility associated with whether you took your umbrella when it rained, and if you took your umbrella and it didn't rain. Okay, so there's some numbers associated with that. Okay, so that's how you represent a decision network. So more formally, you have these kind of nodes which we indicate with circles. So these are like random variables. So more generally, you can have an entire base net over here. You can have a whole graph with all kinds of relationships. But we'll just start off with a simple example where there's just a single random variable, a single node, and these are like the action nodes. Okay, so these are not random quantities, but these are some kind of decisions that you have to take. And there's this utility node. So this is not exactly okay. In some sense, it's random because there's a dependence on a random variable. But these, it doesn't have a distribution per se. It's a number which depends on the random variable and the decision you take. So, for example, you can have things like this. Your decision about, the umbrella node is whether you want to take your umbrella or you want to leave it at home. Okay, so these are two options for the umbrella node, and whether maybe there are two options here. So one is it's sunny or it can be rainy. So there's a probability. So let me call this as a random variable W, and there's a probability associated with W. So maybe something like this. It's sunny with probability zero point 0.7 and it rains with probability zero point 0.3. Okay, so this is something that you have. And more generally, it's a base net. So you have all these conditional probability tables associated with this part. And there is this utility node. So what this means is, for each action, so for each value of umbrella and depending on what the weather is going to be, you have a number. So maybe something like this. If you take your umbrella and the weather is sunny, so this is not very useful because you just had to carry your umbrella around. So the utility is maybe okay. So the two use. So this is umbrella and this is the utility. Okay. So this could be something like say since you had to just carry it around, so maybe something like -10. Okay, and maybe if you take the umbrella and it rains, so there's a lot of benefit for you, so maybe here the benefit is something like 100. Okay, now if you leave your umbrella at home and it is sunny, so you're kind of neutral, so maybe your benefit is like 0 probably. If you leave the umbrella at home and it rains, so maybe here it's something like minus 100. Okay, so let me just give some different numbers so that it doesn't. Yeah, so -10, 80, 0, and -100. So you're affected a lot when it rains and you leave your umbrella at home. So something like this. These are the kind of things that you get from a decision network. And now you have to see what is the action to take, whether you want to take your umbrella or you want to leave it at home. Okay, so one thing is, if you decide to take, so if the action is take, right? So the expected utility. So now there are different things that can happen depending on what the weather is going to be. So what we represent this is the expected utility given, expected utility of the take action. So this is basically all possible values that the weather can take. So all possible values of weather times the utility. So this is this table, okay? This utility of take action and weather is W. Okay, so all possible outcomes that can happen for the weather and the utility. So it's the expected value. So this is the expected utility. Okay, expected utility of take. Okay, so can you tell me these numbers?
0.7 into -10
Yeah, zero
plus
point 0.7 into minus 10
80.
plus zero point 0.7 into 80,
Point
right?
3 into
Zero
80.
point 0.3, right? So it's rain, correct. So zero point 0.3 into 80. So this will be minus 7 plus 24. What's this value?
17.
17, right? Yeah, 17. Okay, so this is the expected utility of take. Now, similarly, you can compute the expected utility of leaving your umbrella at home. Uh, so this one will be again zero point 0.7 into, so the probability that the weather is sunny times you leave it at home. So here it is 0 plus zero point 0.3 times it rains and you leave the umbrella at home. So it's minus 100. Okay. So here the expected utility has become negative. So this is, what is it? So it's minus 30, right? Yeah, minus 30. Okay. So here it's very obvious the best decision to take. If you didn't know anything, like if you didn't have any information, the best value, so best action here is to take your umbrella. So best action is take. And so more formally, this is represented as, the maximum MEU. Okay, so the MEU, so this is the maximum expected utility. Okay, and so just some jargons here because we're just developing the theory, so that's why you have some things here. So this is the maximum expected utility associated with having no information. So this is like there's no information on any quantity in the network. Okay, so you don't know anything about the weather beforehand. In this case, the only random quantity is the weather, and you don't have any information here. And in this case, what you need to do is take the maximum of all the possible actions that can arise, right? And so this is just max of 17 and minus 30. So the value is 17, and this corresponded to the action peak. Okay, so that's what this is. So this is like expecting max. Okay, it's kind of like what you saw in the initial part, right? So you started off initially, you had to decide what action to take. And depending on that, there was a chance node which came in, right? There was a random quantity and that behaved in some way and you got some values. So in this case, the action here was take or leave, and the chance nodes here or the random quantities was the weather. The weather was playing the role of the random agent, right? So the weather could be sunny or rainy, and you had these two, you had some numbers here, right? So this is exactly that. We just wrote it in a slightly different way. Okay, so now, yeah, this is the case when you have one variable. Now, suppose there are some more interactions going on in this network. So you have some more random variables, and there's some things to observe, some things you don't observe. Okay, now how do we generalize this idea of expecting max? Okay, so that's what is about decision networks. So let me just write this part again. Now we'll just bring in a new random variable. So we'll just use these numbers. But now, okay, so So let this be here. So this is the the probability table for weather. And maybe now there's one more random variable like forecast. Okay, so this is like some prediction which has been there. Some scientists are able to predict the weather, and so there's a forecast random variable. And so this part is a base net, right? So the weather and forecast they're related in some way. And so what you have is, depending on how good your forecast is, you have this conditional probability table, right? So maybe something like this: the forecast. So let me write it as maybe like this: weather forecast and the probability of f given w. So you can have like the weather is sunny, and the forecast, maybe the predictions are good or bad. So forecast can be like good or bad. So good means it's sunny, it's a nice weather, and bad is like it's rainy weather. So assuming it rains really horribly to mess things up. Okay, so that's why it's a bad weather. So here, so probability of forecast being good given that it's sunny. Maybe your focus, your prediction is good. So maybe this is like zero point 0.7. And if it is sunny, the forecast being bad, right? So what would this be? This is a conditional probability. So what can we say about this value? Okay, am I audible?
0.3 ma'am only.
Point 0.3. Okay, yeah, that's right. So point 0.3. And maybe something like this. So the weather is rainy, and then the probability that the forecast is good is something like maybe point 0.2. This rarely happens, maybe. And if it is bad, this probability is zero point 0.8. Okay, so this can be a conditional probability table. Now, suppose you observe forecast, right? So suppose you're going to actually see the value forecast, because you know in the start of the day what the prediction is, right? And now you want to make a decision, right? So again, you can compute these quantities. So remember what you did here, you took the expected utility associated with each action. So the same thing you can do here, but it's just that you now have this additional knowledge about forecast. Okay, so let's see what happens if so suppose the forecast is good. Okay, so suppose the forecast is good. Okay, so if that is what you see, now the expected utility of, let's say, the action take, right? If you are going to take your umbrella, given the forecast is good, right? So what is this going to be? So remember, the utility depends on the weather and your action. Okay, so again, there's a probability component here because you still don't know the weather, right? So what you can do is you can just take the probability. What did we do earlier? If we didn't have this information of focus, you just took the probability of the weather, depending on the values of weather, times the expected utility. But now you have this focus, so what you can do is you can take this conditional probability, right? Times the utility of take and this value w, right? So and some overall possible values of w. So more specifically, this would boil down to probability of weather being sunny given forecast is good, times the utility of take. You take your umbrella and the weather is sunny, plus the probability of weather is rainy given the forecast is good, times the utility of take and it is rainy. Okay. Right? So, yeah, so this is how you would compute if you had focused information. Now, the only difference is in these probabilities, right? So, with more information, you compute this conditional probability. Now, how do we compute this conditional probability here? So, can you compute this and tell me these numbers? So here the network gives you weather and forecast given the weather. So how do I get weather given forecast? Okay, I need a response.
Joint probability of W and F upon P of W.
Yeah. So let me just go down. So okay, so probability of weather is sunny given the forecast is good. Yeah, so this is like the joint probability. W is sunny and forecast is good divided by probability of forecast is good, right? So yeah, this is how you'd compute it. Now, in general, this is an inference kind of question, right? So in the last few classes, we've been doing base nets and inference. So here it's fine. It's just two variables. So, you can just compute it using the base rule. But more generally, these kind of probabilities, this is an inference in a base net. Okay. So you can use the ideas we did, like you can use variable elimination to compute these probabilities. Okay. So can we just do that for this example? So what did we have to do? Like we had the initial tables, right? Probability of weather and probability of F given W. We had that. And what did we do in variable elimination?
Join
We did a join, right? So that would give you what?
joint
Let's
of
see.
F and W.
Yeah, joint of this. So maybe let's just do some computation so that we get some numbers here. So can you quickly do this and let me know? So maybe let me just copy this a little down. Okay, so yeah, so a join would be so join of F and W, right? That would be like get the same table, sun good, sun and bad, rain, yeah, rain good and rain bad. Okay, and what will these numbers be? So this will be P of FW. It's a join over W. So what are these numbers?
0.49.
So this is 0.49. Yes. Sun and bad.
0.21.
So this and this one. So 0.21. Okay.
0.06.
Rain 0.06 and
0.24.
0.24. Yeah. So these are the numbers. And so what are you going to get here for weather equals, okay, so this probability, this conditional probability here, you can get by, again, doing a normalization here, right? So this is the forecast and this is the weather. So can you tell me these numbers now? So basically these two you have to sum up, right? Okay. Bad numbers to do, but anyway, can you, uh, what's this value going to be? 49 by sum of this, right? Okay, can you tell me the values?
0.89.
So the first one is 0.89.
Yes.
Okay. And this one. So this is probability of W given F equal to good.
0.109.
0.109. Okay. So I'm just taking it by faith, okay, Advait, with what you have said.
Yes.
Uh, okay. So this value here is now 0.89. Okay. Probability of weather is sunny given the forecast is good. So that value you can plug it in here. And again, you have these. So this value is going to be 0.89 times utility of take and sunny. So that is minus 10, right? And plus 0.109, so that is this value, times utility of take when it was rainy, so that was 80. Okay, so what is this number? Can you tell me this?
0.109. It's written.
This is 0.108. So this is a, you get the same value. No, I'm saying like this total sum, right?
Oh, okay, sorry. Minus 0.18.
Minus 0.18. Okay, okay. Is that right? Okay, fine. So, okay, suppose this is fine. I mean, okay, I'm just not checking the values. Okay, so this is how you compute it. And suppose this is minus 0.18. So this is the case when the forecast is good. So what we have computed is the expected utility of take given the forecast is good. So this value is minus 0.18. Now, similarly, what you can do is you can find the expected utility of leaving your umbrella given the forecast is good. Okay, so the same approaches you can use to do this. And so, what you have to do, so now the value of this information, the forecast being good, so the maximum expected utility of the forecast being good. Okay, so this is just going to be max of these two expected utilities. So the maximum of expected utility of take. So let's just write it as action. So the action, whatever action is there, whatever action is possible, you take that one, and given f is equal to good, right? So this is you'll get some number here. Now similar thing you can compute for the case when the forecast is bad, right? So this is a lot of computation that's there, but finally you can get the expected utility in the same manner. So what you do is you just take the action as leave now instead of sorry, not leave. So the f is bad. So what you do is you just take the focus is bad. So in all these places it changes to f is bad, and you find the expected utility of take as well as leave, and you compute the best action from that. Okay, out of these all these possibilities, you compute the best from there, and you get these numbers. Okay, so what these numbers mean is, suppose you had some information. If you knew that the forecast was good, what is the best you could have done? What's the best action you could have taken? If the forecast was bad, you knew this information, what's the best you could have done? Okay, now there is an other quantity which is maximum expected utility of the forecast random variable itself. Okay, so this is now, I mean, you might have guessed it already. Now you don't know what, if you don't know what the forecast was going to be, but you're trying to account for all possible values of forecast. What you could do is you can take all, again, an expectation over the forecast random variable. So all possible values of f, so probability of f equal to small f, and the maximum expected utility of f equal to this value. Okay, so this is actually the overall maximum expected utility of the random variable f. Right. So maximum expected utility of the random variable f. Okay, of the random variable f. So it's like an average. It's exactly an average over what happens at best if you knew the forecast. Okay, so now there's this concept of value of perfect information. So what it means is, if you knew the forecast, there's some utility associated. But suppose you didn't know that, what you would have done is, what we just computed initially. So this value, MEU of, if there was no info, this is what you would have done. Whereas if you knew the focus, you would have done something else. So what's the difference in these two? So that is what is value of perfect information. So the value of perfect information. Um, so in this case, let's just write it. So VPI of the random variable f. Okay, so this is a value of perfect information associated with f, associated with the random variable f. So this is the maximum expected utility of f minus the maximum expected utility of, if you knew nothing. Okay, so so this is like a difference in paradigms, like it's basically the state of information and what you could have done if you knew versus if you didn't know. Okay, so many times this has the interpretation of how much you're willing to pay, right? If you knew the forecast information, what is it that how much are you willing? Suppose you have to pay to get the forecast information. So how much are you willing to pay? So this is a number which kind of signifies that, and that's why it's called a value. Okay. So what do you expect? Is this number going to be greater than zero, less than zero, or equal to zero? Generally, what do you think is going to happen?
It should be more,
It
not
should
less.
be more, right? Because if you know the forecast, on an average, you expect to do better, right? So so this is always going to be a greater than zero value. Yeah. So if you didn't know anything, there's some action that would have been best, and that action is also valid to take if you knew the forecast. So it cannot be less. I mean, if you know the forecast, you cannot do worse, right? I mean, that action is still a valid action. Okay, so in every random variable, you expect it to be greater than or equal to zero, the value of perfect information. Now, sometimes it can be equal to zero. So, any thoughts on when this can be equal to zero? When can it be zero?
When the variable is like disjoint from the rest of the network.
Exactly, right? So if you had something else here, right? So something which, it's not impacting the weather in any way, right? So in that case, this very, I mean, so you don't expect, knowing this to, add any information about weather. So in that case, you expect, I mean, the value of perfect information is zero. And more generally, I mean, it's one case is yes, if you have something which is disjoint, it is zero. The value of perfect information is zero. But you could also have something here. So maybe some variable over here, right? So, so this goes back to what we learned in base nets. So if it is conditionally independent of weather, right? If you know forecast, and then if you add some additional information here, okay, that's not going to add anything more about weather because weather is conditionally independent of this variable given the forecast, right? So in that cases, so what you do is you look at the parents of the utility node, and if your new random variable is disjoint or it's conditionally independent of the parent, then you don't expect to get any new information from here. Okay, so this is another random variable A. Okay, so so that's the general idea of value of perfect information. So what you can do is you can kind of use it to see, like, sometimes people like to ask for information, right? And so whether you really need to know this information, this random variable A, whether you need to know this instantiation or not, that is something that you can use this kind of a network to deduce that. Okay, and more generally, you can have different parents here. So maybe the utility is function of not just the weather, but maybe some other random variables also. Okay, so maybe there can be these kind of random variables in your network, and the utility depends on all of them. So what you need to do in general is, when you compute these probabilities, you need to look at all these parents, the weather, the value of B, the value of C, and you need to look at this joint. Okay, so something like this, C equal to C, and overall W, B, and C. Okay, so that's something, I mean, a more general representation would have all of that. Okay, and that's how you compute these numbers. And the significance of this is, knowing some information can change your action. Okay, so maybe let's probably just complete this example here. I introduced these terms, but maybe I think we should just finish these computations to see really what's going on. Okay, so can you tell me these values for, leave given forecast is good also? So I think we need to compute a couple of things, right? So, okay, so expected utility of leave given the forecast is good. So here what you need to do is probability of weather equal to sunny given forecast is good. uh, times the utility of leave and sunny plus probability of weather equal to rain given forecast is good times the utility of leave and rain. Okay, so can you tell me what these numbers evaluate to?
minus 10.9.
So this is the overall number.
Yes.
Okay, minus 10.9. Okay, fine. So this is, yeah. So if you knew the forecast was good, the better action was to, so as per this, it is to take, is it? That's how it's boiling. Okay. So why did that happen? So take with rain, just a second. Huh? So, okay, I think, yeah, this kind of dominates. So that's what is going on here. Okay, so here, okay, so these are like screwed up numbers. I mean, the setting here probably is a bit screwed up. But anyway, let's just work it out. So here, what it's telling you is if the forecast is good, the best action is to take your umbrella. Best action is still to take. Okay. All right. So now let's also do this one. Expected utility of take given the forecast is bad. Okay, so I think we need to compute. Okay, so we have these numbers here, so we can compute the probabilities also. So this would, can you tell me what the numbers you need to compute are, the probabilities here? What is the, what all values do you need here?
Take given f equal to bad into
Uh,
utility of.
so here it's the probability of weather. So the parent of this utility node, so that is weather,
Oh, sorry.
right? So probability of weather is sun
Then
given
given
f is
f is
bad,
bad
yeah,
into
times
utility of take into sun.
take sun, yeah, plus probability of weather is rain given f is bad times the utility of take and rain. Okay, yeah. So what will these numbers be? So probability of weather sun given forecast is bad. So here, right, you need to do a normalization over bad. So what would these probabilities be?
0.466.
This one is 0.466, okay, and this one
0.533.
0.533. So yeah, one minus that. Yeah. Okay, so right, so now where were we? Yeah, this value, right? Probability of whether sun given forecast is bad. So that is this one, 0.466. Right? So 0.466 times what's the value? Utility of take and sun. So it's minus 10 uh, plus probability of weather is rain given. So this was 533, right? 533 times utility of take and rain, which is 80. So this value. Where did I write it? Yeah, into 80. Okay, so can you do this computation and let me know?
38.00. Like 38 approx.
38. Okay, okay. So this is expected utility of take. Now similarly, you need to do expected utility of leave given forecast as bad. So let's just do this one so that you know everything is clear and the overall picture is clear. So what does it boil down to? So here you need to take probability of wet. I mean, all these remain the same. So 0.466 times the utility of leave and sun plus 0.533 times utility of leave and rain. Right. So what numbers did we use here?
0 and
0.46.
minus 100.
So this was 0 and this was minus 100, is it?
Yes.
minus 100. So this will give you minus
3.3.
minus 53.3, right? So yeah, so what this means is now the takeaway here is if the forecast is bad, then the best action is again to take. Okay, so best action is to take your umbrella. Okay, so this is maths of basically 38 and minus 53. Okay, so I don't know, in this case, probably, this focus is not helping. So here also the best action was take if you didn't know any information. And here, irrespective of what the focus is good, also best action is to take. If focus is bad, also the best action is to take, right? So I think the VPI will be 0 here. Perhaps a bad way of setting the numbers. Uh, okay, so okay, so Okay, so let's just compute the maximum expected utility of the focused random variable. So here what you need is, okay, so now you need to do one more set of operations to find the probability of f. Okay, so w and f given w is there. So now you need to find the probability of forecast. So remember this was probability of forecast equal to good times MEU of forecast equal to good, this case, and plus probability of forecast is bad times the maximum expected utility of the forecast equal to good. Okay, so maximum expected utility of this value forecast is good. So that was what forecast is good. So it was minus 0.18. Right? So minus 0.18, and this value. Okay, I'm writing something else. So here is focus is bad. So maximum expected utility of a bad focus, this is 38. And you need to weigh this by both these terms, right? So, okay. So can you compute this probability of the focus being good or bad from these tables? So again, that is also an inference question, right? From the base net,
Eliminate W from the join.
from this, right? So eliminate W. So can you tell me the value? So focus good will give what? And focus bad
0.55 and 0.45.
0.55 and 0.45. So this will be 0.55. Where did I write this? Yeah. So 0.55 times minus 0.18 plus 0.45 times 38. And this value is what?
Seventeen.
17? 17, right? Wait, you said 17?
Yes, yes.
Yeah. So you got 17, and so what was the value? I think that was also 17. Right? Yeah, so it matched this value here. So what this means is that the value of perfect information for forecast. So this is MEU of f minus MEU if you didn't know anything, right? So that is actually 17 minus 17 is 0. So it's this particular way in which we model the utilities, so that ensured that this forecast didn't really impact. Knowing the value of focus is not helping here. Okay, so yeah, I mean this is because of the bad values we took for utilities. So maybe try some other values. Maybe try to take this as 10, 80, and maybe yeah, keep this as 0 and minus 100 itself. Just as an exercise, just see what happens here. So if the utility is this, see what happens. So generally, if you know something about some other random variable, your decision should change. Your action, what is the best action, should change. In this case, it so happened that your best action is not changing. It's always to take, irrespective of whether you had. So that's why the value of perfect information is becoming 0. Okay. All right. So, are there any questions? I mean, the class has been very quiet. Advait has been interacting and really grateful. But what about the others? Are there any questions here? Is this clear what we're doing? It's clear? Yes. It's a simple concept. It's just you have to do the computations properly. That's the only thing. Okay, and yeah. So yeah, okay. So just try this out as a homework. And more generally, maybe I'll try to put up one more question for, I'll probably release one more assignment where, I can give you another question, maybe a slightly bigger network with several random variables. Okay, and you can try to get some practice on this. Okay, so all right. So I think we'll stop a little early today. So thanks everybody for coming. And we'll meet again on Tuesday. Okay. So I'll just hang back if there are questions and raise thanks.